March 19th, 1945. Kasumigaura, Naval Air Technical Arsenal, 60 miles northeast of Tokyo. Lieutenant Commander Minoru Genda stood before an aircraft that represented everything wrong with Japan's position in this war. The bent-wing silhouette was unmistakable even at a distance. An American Vought F4U Corsair fighter, captured intact after a forced landing near the base 3 weeks earlier. Japanese ground crews had patched bullet holes in the wings with fabric, cannibalized parts from crashed Corsairs found elsewhere, and somehow coaxed the damaged fighter back to airworthy condition. Now Genda, one of Japan's most experienced test pilots and a veteran of hundreds of combat missions, would fly it. He walked slowly around the aircraft, noting details that intelligence reports had mentioned, but that no Japanese pilot had seen firsthand on a functioning example. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The inverted gull wings, designed to accommodate an enormous propeller while keeping the landing gear short, the massive Pratt and Whitney R-two 1800 Double Wasp engine, the 650 caliber machine guns, 3 mounted in each outer wing panel, everything about the Corsair radiated power and purpose. American ground crews had abandoned this particular aircraft after engine failure forced an emergency landing during a strike mission against targets near Tokyo. The pilot had escaped, leaving behind an intact fighter that Japanese recovery teams found the next morning. Within hours, the aircraft had been transported to Kasumigaura, headquarters of the Imperial Japanese Navy's Aviation Technical Intelligence Operations. For 3 weeks, teams of engineers and mechanics had worked to restore the Corsair to flying condition. They studied every system, measured every component, documented every design feature. What they discovered in those 3 weeks of intensive examination had profound implications, but it was the specifications for the armament that caused the most disbelief among Japanese aviators who reviewed the technical reports. 6 Browning M2 aircraft machine guns, each gun capable of firing between 750 and 850 rounds per minute, 6 guns firing simultaneously. The mathematics were straightforward, but the conclusion seemed impossible. 4,800 rounds per minute, 80 rounds per second. The Corsair could deliver more firepower in a 5-second burst than a Japanese Zero could fire in an entire 30-second ammunition load. Japanese fighter pilots who read these specifications reacted with skepticism bordering on dismissal. The numbers had to be exaggerated, American propaganda perhaps, or a misunderstanding of the weapon specifications. No aircraft could mount such firepower. The weight alone would be prohibitive. The recoil would tear the wings off. The ammunition requirement would be impossible to carry. The disbelief was understandable given Japanese combat experience up to early 1945. Japanese fighters had dominated the skies over the Pacific for the first year of the war. The Zero's exceptional maneuverability and range had devastated Allied air forces from Pearl Harbor through the Dutch East Indies campaign. Japanese pilots had grown accustomed to fighting enemies with inferior aircraft and inadequate training. But by 1943, the situation had shifted dramatically. New American fighters appeared in increasing numbers: the F-6F Hellcat, the F-4U Corsair, the P-38 Lightning. These aircraft possessed speed, firepower, and durability that Japanese fighters could not match. Pilots returning from combat in the Philippines and Formosa reported that American fighters simply destroyed Japanese aircraft with single bursts of fire. A Zero hit by a Corsair didn't limp home damaged. It disintegrated, wings sheared off, fuselages broke apart. Pilots had no chance to bail out. The aircraft simply ceased to exist as functional machines. But the specifics of how the Americans achieved this overwhelming firepower advantage remained unclear until the captured Corsair arrived at Kasumigaura. Genda had heard all the arguments and speculation during the briefings. He had seen the doubt in the eyes of younger pilots, who believed their training officers' claims about American industrial weakness and material inferiority. Now he would discover the truth firsthand. He climbed into the cockpit and immediately noticed how different everything felt from Japanese aircraft. The seat sat higher in the airframe than any Japanese fighter. Forward visibility over the long nose was poor for ground operations, but would be excellent once airborne. The control stick felt solid, built from heavier materials than Japanese equivalents. The rudder pedals were spaced wider apart, designed for larger American pilots. The instrument panel displayed English markings that Genda had studied during the preparation period. Airspeed indicator graduated in miles per hour rather than knots. Altimeter reading in feet. Engine instruments using American measurement standards. Everything foreign, yet the basic layout was logical and functional. The gun sight was particularly interesting. A simple reflector sight, similar in principle to Japanese designs but built with heavier construction and clearer optics. The trigger on the control stick felt different too. Heavier spring pressure than Japanese guns, more deliberate. The Americans apparently didn't believe in hair triggers. Ground crew started the engine using an American-style procedure that differed from Japanese methods. The 2800 roared to life with a deep, powerful sound that reverberated across the airfield. 18 cylinders arranged in 2 rows, each cylinder producing more power than Japanese engineers thought possible from air-cooled radial designs. Genda ran through the engine checks, watching gauges carefully for any indication of problems. Pressure good. Cylinder head temperatures within limits. Manifold pressure steady. The engine ran smoothly despite the repairs and cannibalized parts. American engines, the technical team had concluded, were designed with such generous tolerances and safety margins that even damaged examples continued functioning reliably. He released the brakes and taxied toward the runway. The Corsair's long nose made ground visibility poor, forcing him to S-turn while taxiing to see ahead. A common problem with powerful fighters, the Japanese Army's Ki-84 Frank suffered similar visibility issues. At the runway threshold, Genda performed a final control check and engine run-up. Everything appeared normal. He advanced the throttle, and the Corsair accelerated down the runway with impressive force. The massive propeller, 13 feet 4 inches in diameter, was the largest fitted to any single-engine fighter in widespread service. The propeller alone weighed more than some entire Japanese fighter engines. It transformed the R-2800's power into thrust with remarkable efficiency. The tail came up quickly, and the Corsair lifted off after a remarkably short ground roll. Genda raised the landing gear and felt the aircraft accelerate as drag decreased. The gear retracted cleanly into the inverted gull wing sections, a design feature that kept the landing gear struts short and light while accommodating the enormous propeller. He had flown the Zero, the Shiden, the Raiden, the Frank. He knew Japanese fighters intimately. The Corsair felt different. Heavier. More solid. Less nimble in the initial impressions but with reserves of power that Japanese fighters lacked. The controls responded with deliberate precision rather than the hair-trigger sensitivity of the Zero. He climbed to altitude, noting the climb rate. The Corsair ascended at over 4,000 feet per minute, exceptional performance that exceeded any Japanese fighter currently in service. The engine delivered power smoothly throughout the climb with none of the temperamental behavior that plagued some Japanese designs. Japanese engines required careful throttle management, precise mixture control, and constant monitoring to prevent overheating or detonation. The Corsair's engine simply ran at whatever power setting Genda selected. At 10,000 feet, Genda leveled off and began basic handling tests. The Corsair responded to control inputs with deliberate precision, not the lightning reflexes of the Zero, but controlled and predictable. Aileron response was good at this speed. Elevator authority felt solid. Rudder required more force than Japanese fighters but gave positive directional control. He tried a barrel roll. The Corsair rolled through the maneuver smoothly, not as quickly as a Zero or Shiden at slow speeds, but with power and stability that would make it deadly in a sustained rolling fight at high speed. Japanese fighters could outturn the Corsair at slow speeds below 250 miles per hour, but at the combat speeds where most engagements actually occurred, the advantages were less clear. The Corsair maintained full control authority at speeds where Japanese fighters' controls stiffened or became unresponsive. Genda pushed the Corsair to maximum level flight speed, watching the airspeed indicator climb past 400 miles per hour. At these speeds, the Zero's fabric-covered control surfaces ballooned with air pressure, making the aircraft sluggish and difficult to maneuver. The Corsair's all-metal control surfaces, hydraulically boosted, responded instantly to stick inputs, even at maximum speed. This single characteristic explained much of the Corsair's combat success. American pilots could fight at speeds where Japanese pilots could barely control their aircraft. If a Japanese pilot found himself in a disadvantageous position, he couldn't simply push the stick forward and dive away at maximum speed because his controls would become too stiff to maneuver. American pilots faced no such limitation. Then Genda tested the aspect that would define his report and influence every subsequent discussion of the Corsair's capabilities. He armed the guns, selected all 6, and pointed the nose at a designated area of ocean far from shipping lanes. The armourers had loaded the guns with a standard American combat mix: 2 rounds of ball ammunition, 2 rounds of armour-piercing incendiary, 1 tracer. The pattern repeated throughout the ammunition belts. He pressed the trigger. The Corsair shuddered. The nose dipped slightly from the recoil despite the aircraft's weight and power. The sound was unlike anything Genda had experienced. Not the sharp crack of Japanese machine guns or the slower thump of cannon. This was a sustained roar, a continuous hammering that went on and on as long as he held the trigger. He fired a 3-second burst. The tracers formed an almost solid stream of fire reaching toward the target area. He released the trigger and the guns stopped instantly. No residual rounds cooking off, no jamming, no malfunction, just immediate, reliable cessation of fire when he released pressure on the trigger. He fired again, another 3-second burst. Then a longer 5-second burst that consumed what he estimated to be 400 rounds based on the rate of fire. The recoil was substantial but manageable. The aircraft remained controllable throughout. More than controllable, actually. The Corsair's weight and powerful engine meant that the recoil, while noticeable, had minimal impact on aircraft handling or aim. A Zero firing its 20mm cannon experienced significant recoil that disrupted aim and required the pilot to compensate. The Corsair's designers had built the airframe strong enough and powerful enough that 650 caliber machine guns firing simultaneously caused manageable vibration, but didn't significantly affect the pilot's ability to keep the gun sight on target. The destructive effect of such firepower was not immediately visible from the cockpit. Genda couldn't see what those bursts would do to an actual target, but he understood the implications. Each 50 caliber bullet weighed approximately 1.6 ounces. At 750 to 850 rounds per minute per gun, 6 guns delivered approximately 80 bullets per second to the target area. In a 5-second burst, 450 caliber rounds would impact the target. Each bullet traveling at 2,800 feet per second, with enough kinetic energy to punch through aluminum skin, shatter structural members, rupture fuel tanks, and destroy control systems. No Japanese aircraft could survive that volume of fire. The Zero's thin aluminum skin and minimal internal structure provided no meaningful resistance to 50 caliber armor-piercing incendiary ammunition. When Genda landed 40 minutes later and climbed from the cockpit, the intelligence officers and engineers surrounded him immediately, demanding observations and impressions. He spoke carefully, choosing words that would appear in official reports and influence tactical doctrine. The Corsair's speed is approximately 425 miles per hour in level flight at optimal altitude, faster than our Zero, Shiden, or Frank fighters by significant margins. The Americans can dictate engagement terms based on speed advantage alone. Japanese fighters cannot catch a Corsair in level flight or climbing. The climb rate exceeds our best-performing aircraft. An American pilot who converts airspeed to altitude can disengage from any combat at will. Our fighters cannot follow. The Corsair pilot chooses when to fight and when to extend away. We cannot force combat on an unwilling Corsair pilot. The turning radius at combat speeds is comparable to our heavier fighters. The Zero can turn inside the Corsair in sustained turning combat below 250 miles per hour. But the engagement must occur at slow speeds, which gives the initiative to the American pilot. He can choose whether to slow fight or maintain speed advantage. Combat experience indicates American pilots are trained to avoid slow-speed turning fights. Then Genda addressed the armament question that everyone wanted discussed. The firepower specifications are accurate. 650 caliber machine guns firing simultaneously produce approximately 4,800 rounds per minute. I fired 3 bursts, totaling approximately 11 seconds. That consumed perhaps 900 rounds. Each burst delivered more rounds than a Zero can carry for a single gun during an entire mission. One of the younger intelligence officers, a lieutenant who had never faced American fighters in combat, interrupted. Respectfully, Commander, that seems impossible. The recoil alone would make the aircraft uncontrollable. Our engineers calculated that such firepower would require structural reinforcement that would make the aircraft too heavy to be combat effective. Genda's expression didn't change, but something in his eyes silenced the lieutenant immediately. I have just flown the aircraft. I have fired the guns. The specifications are accurate. The recoil is substantial but manageable, because the aircraft weighs over 12,000 pounds fully loaded, more than twice the weight of a Zero. The Americans built the aircraft strong enough to handle the recoil of this armament package. The weight penalty is compensated by the 2,000 horsepower engine. The engineering team had already analyzed this design philosophy during their examination of the captured Corsair. Japanese fighter design prioritized lightweight to maximize maneuverability and range. Every component was designed to minimum weight tolerances. The result was aircraft that could perform remarkable aerobatic maneuvers, but were fragile and lacked growth potential. American fighter design accepted weight penalties in exchange for protection, firepower, and structural strength. The Corsair carried armor plate behind the pilot's seat, self-sealing fuel tanks that could absorb bullet hits without catastrophic fires, robust structural members designed to handle battle damage and hard carrier landings. All of this added weight, but the powerful engine compensated. Another engineer raised the question of ammunition capacity. How much ammunition does the Corsair carry for these guns? The technical documentation provided the answer. 400 rounds per gun for the inner pair, 375 rounds for the outer guns. Total ammunition load of 2,350 rounds. At the maximum rate of fire, this provides approximately 30 seconds of continuous firing time. The room fell silent as officers performed the mental arithmetic. 30 seconds. A Zero carried 60 rounds per gun for its 220mm Type 99 cannon and 550 rounds per gun for its two 7.7mm machine guns. The cannon fired at approximately 500 rounds per minute combined, the machine guns at approximately 1,000 rounds per minute combined. Total firing time for all weapons was approximately 33 seconds if the pilot fired everything continuously. But the comparison understated the disparity. The Zero's 33 seconds of firing time assumed continuous fire from both machine guns and both cannons simultaneously, which was never done in practice because it wasted the limited cannon ammunition. In actual combat, pilots fired the machine guns to adjust aim and used the cannon for short bursts only when they achieved a good firing solution. Effective firing time for the cannon was perhaps 7 to 8 seconds before ammunition exhaustion. The Corsair's 30 seconds represented 6 guns firing simultaneously, delivering 4,800 rounds per minute. In 5 seconds, the Corsair fired 400 rounds. To deliver 400 bullets, a Zero would need to fire both machine guns continuously for 12 seconds, assuming no stoppages. The cannon, at 500 rounds per minute combined and 60 rounds per gun total, would be exhausted in 14 seconds of continuous fire. The implications extended beyond simple firepower comparison. The engineers who had examined the Corsair's construction now presented their findings to complement Genda's flight test observations. The revelations were sobering and revealed patterns that extended far beyond armament. If you find this story engaging, Please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The armament installation demonstrated American design philosophy at its clearest. The 6 machine guns were mounted in the outer wing panels, 3 per side, with the ammunition boxes positioned inboard near the fuselage for better weight distribution. The installation was clean, well-engineered, and designed for field maintenance rather than factory-level service. Each gun could be removed and replaced in minutes using basic tools. The ammunition feed systems used standardized components throughout. Electrical firing solenoids were identical for all 6 guns, meaning a single spare part could replace the firing mechanism on any weapon. The feed covers could be opened quickly for clearing jams or inspecting the ammunition belts. Link ejection chutes directed spent brass and belt links away from critical flight surfaces. Everything about the armament installation emphasized simplicity, interchangeability, and ease of maintenance. This was a weapon system designed to be serviced by mechanics with basic training, not specialists with years of experience. An experienced American armorer could reload all 6 guns and perform basic maintenance in under 20 minutes. A crew of 2 armorers could perform a complete ammunition reload in under 15 minutes. The contrast with Japanese armament installations was stark and illustrated fundamental differences in design philosophy. Japanese fighters used a mix of machine, guns, and cannon, each type requiring different maintenance procedures, different spare parts, different specialist knowledge. A Zero carried 2 7.7mm machine guns synchronized to fire through the propeller arc and 2 20mm cannon mounted in the wings. The 7.7mm machine guns were essentially Japanese-manufactured copies of British Vickers designs, modified to use Japanese ammunition. The synchronization gear that allowed them to fire through the propeller arc without shooting off the blades was mechanically complex and temperamental. The gear required precise timing adjustment, and the slightest error could result in the guns shooting off pieces of the propeller or failing to fire at critical moments. Field maintenance on the synchronization system required skilled specialists who understood the intricate mechanical timing mechanisms. The gears wore over time and with use, requiring constant adjustment and eventual replacement. In forward operating areas with limited maintenance facilities, keeping the synchronized guns functioning properly was a constant challenge. The 20mm Type 99 cannon were even more problematic. Based on Swiss Oerlikon designs, the cannon used a complex drum magazine system that was prone to jamming. The ammunition drums required careful loading in a specific pattern, and any error in loading could cause the weapon to malfunction during combat. The cannon's firing mechanism was mechanically sophisticated, but reliability suffered in field conditions with exposure to moisture, dirt, and temperature extremes. Pilots frequently complained about cannon failures during combat. A pilot might line up a perfect shot, press the trigger, and experience a failure to fire because of ammunition feed problems, firing mechanism malfunction, or synchronization issues. Japanese pilots learned to fire short test bursts before engaging targets to ensure their weapons were functioning, but even this precaution didn't guarantee reliability when it mattered most. The maintenance burden extended beyond the weapons themselves. Japanese aircraft required skilled mechanics for virtually every aspect of servicing. Engine maintenance demanded technicians who understood the intricate timing and adjustment procedures required to keep temperamental Japanese engines running properly. Control surface maintenance required craftsmen who could repair fabric-covered surfaces and ensure proper tension and alignment. Field repairs on Japanese fighters often required fabricating custom parts or adjusting components to fit specific aircraft. No 2 Zeros were truly identical, despite coming from the same production line. Minor variations in manufacturing tolerances meant that parts from one aircraft might not fit another without modification. This was accepted practice in Japanese aircraft production, where skilled craftsmen were expected to fit and adjust components during assembly. The Corsair represented a completely different manufacturing and maintenance philosophy. Every part manufactured to precise tolerances measured in thousandths of an inch. Every component interchangeable between aircraft. Any .50 caliber machine gun from any source would fit any mounting position in any Corsair. Any ammunition feed mechanism would work with any gun. Maintenance was simplified to the point where relatively inexperienced mechanics could perform complex repairs using standardized procedures and pre-manufactured replacement parts. This standardization extended throughout the entire aircraft. Hydraulic fittings used consistent thread patterns. Electrical connectors were standardized. Instruments and controls were identical across aircraft. An experienced Corsair mechanic could work on any Corsair from any production batch and find everything exactly where he expected it. The maintenance advantages this provided were difficult to overstate. In forward operating areas with limited facilities and inexperienced personnel, American aircraft could be kept operational with relative ease. Japanese aircraft required increasingly specialized maintenance as the war progressed, and experienced mechanics became casualties or were reassigned. But it was the gun specification that continued to dominate discussions among Japanese pilots reviewing the intelligence reports. 4,800 rounds per minute had seemed like propaganda until pilots examined the technical documentation and fired the guns themselves. Several other experienced test pilots flew the captured Corsair over the following days, each performing firing tests to verify Genda's observations. The consensus was unanimous. The firepower specifications were conservative, if anything. The Browning AN-M2 aircraft machine gun was a proven weapon, mature and reliable after years of development and combat use. The 50 caliber cartridge it fired, officially designated the 12.7mm by 99mm, was one of the most effective aircraft armament rounds developed. Each bullet weighed approximately 46 grams and left the barrel at 865 meters per second. The armor-piercing incendiary variant could penetrate Japanese aircraft armor at combat ranges and had a devastating incendiary effect on fuel tanks and flammable materials. The destructive effect on unarmored structure was catastrophic. A single 50 caliber bullet hitting a Zero's wing could tear a hole the size of a man's fist through the thin aluminum skin, 6 guns firing simultaneously, each gun delivering 13 to 14 rounds per second. Combined output of approximately 80 rounds per second reaching the target area. A 2-second burst, short by American standards, would place 160 50 caliber bullets in the area covered by the gun sight. The concentration of fire was sufficient to saw through structural members, sever control, cables, rupture fuel tanks, and shatter cockpit armor. Pilots who had fought Corsairs and survived, a small and diminishing group by March 1945, reported that aircraft hit by Corsair fire often disintegrated, not merely damaged or disabled. Entire sections of wing or fuselage could be blown away by a sustained burst. Japanese pilots, who observed Corsairs attacking bomber formations, described the effect as similar to flying through an aerial chainsaw. One pilot, a veteran of combat over the Philippines, described watching a Shiden fighter take a burst from a Corsair during an engagement over Formosa. The Corsair pilot fired for perhaps 3 seconds. The Shiden's left wing separated completely from the fuselage, not torn away gradually. It simply ceased to be attached to the aircraft. The Shiden rolled inverted and plunged toward the ocean. The pilot made no attempt to bail out. He was likely already dead from 50 caliber hits to the cockpit. The technical team at Kasumigaura now faced the uncomfortable task of explaining these findings to commanders who needed to maintain pilot morale while conveying accurate tactical information. Captain Hikoichi Yamamoto, who oversaw the evaluation program, drafted the official assessment report. His conclusions were precise and devastating to anyone who understood their implications. The F4U Corsair represents a weapon system specifically designed to exploit American industrial strengths while compensating for potential pilot skill deficiencies. The aircraft is fast enough to dictate engagement terms in all circumstances. American pilots can choose when to fight and when to disengage based on tactical advantage. Japanese fighters cannot force combat on an unwilling Corsair pilot regardless of numbers or position. The armament package delivers overwhelming firepower sufficient to destroy any Japanese aircraft with minimal exposure time. A 2-second burst places approximately 160 50 caliber rounds in the target area. Japanese aircraft cannot survive this level of firepower. Structural failure is immediate and catastrophic. Pilot survivability when hit by Corsair fire is effectively zero. The construction is robust enough to absorb battle damage that would disable Japanese fighters. Armor protection for the pilot, rated to stop 7.7mm ammunition at close range, protects against most Japanese fighter armament. Self-sealing fuel tanks prevent catastrophic fires from fuel system hits. Structural members are over-engineered to handle battle damage and continue functioning. The Corsair can sustain multiple hits from Japanese weapons and return to base. Japanese fighters cannot. Most critically, the Corsair's design enables mass production using standardized components and simplified maintenance procedures that require minimal specialist knowledge. The Americans can produce hundreds of these aircraft monthly, using semi-skilled labor and automated manufacturing equipment. Field maintenance requires only basic training and standard tools. The logistics burden is minimal compared to Japanese aircraft. Japanese production methods cannot match this output. Our fighters require skilled craftsmen for construction and experienced specialists for maintenance. We cannot produce aircraft at the rate required to replace combat losses, and we cannot maintain the aircraft we have in service with the diminishing pool of experienced mechanics. Even if we obtained complete engineering documentation for the Corsair, our industrial base is not organized to implement the manufacturing processes required. The report continued with specific tactical recommendations based on Genda's flight testing and detailed analysis of the armament capabilities. The recommendations acknowledged harsh realities that many Japanese officers found difficult to accept. Japanese fighters should avoid head-on attacks against Corsairs under all circumstances. The combined firepower of 650 caliber guns firing forward makes frontal approaches suicidal. A Corsair can fire 400 rounds in a 5-second burst. The probability of being hit in a head-on engagement approaches certainty. No Japanese aircraft can survive flying through that volume of fire. Dogfighting at low speeds offers Japanese fighters their only significant advantage. The Zero and Shiden can outturn the Corsair in sustained turning combat below 250 miles per hour. However, American pilots are specifically trained to avoid slow-speed turning fights. They will use speed and altitude advantage to extend away from unfavorable engagements. Forcing a Corsair into a slow-speed turning fight requires either achieving complete surprise or trapping the American pilot in a situation where speed advantage cannot be employed. Group tactics offer Japanese fighters the best chance of achieving kills against Corsairs. A single Zero or Shiden cannot force a Corsair to fight. The American pilot will simply accelerate away and climb to altitude where Japanese fighters cannot follow. But multiple Japanese fighters attacking from different angles simultaneously can make high-speed extension difficult and force the American pilot into defensive maneuvering that costs energy. Coordinated attacks from multiple directions are essential, but assembling such attacks requires communication and coordination that becomes increasingly difficult under combat conditions. The armament disparity means that Japanese pilots must achieve firing solutions and deliver effective bursts much more quickly than American pilots. A Corsair pilot can afford to fire longer bursts with lower accuracy because the volume of fire compensates for imperfect aim. The cone of fire from 6 guns is wide enough that minor aiming errors still result in hits. Japanese pilots must make every burst count because ammunition loads are limited and firing time is restricted to seconds before exhaustion. Ammunition conservation is critical for Japanese pilots. With limited cannon ammunition, pilots must hold fire until they achieve near-certain hits. The temptation to fire at marginal opportunities must be resisted because wasting ammunition leaves the pilot defenseless. American pilots face no such constraint. The 30-second ammunition supply allows multiple engagements without reloading. American pilots can fire at any target within reasonable range without concern for ammunition exhaustion. These tactical recommendations were distributed throughout Japanese naval aviation units in April 1945. The response among combat pilots was mixed and revealed the complex psychology of warriors confronting evidence of overwhelming technical inferiority. Veterans who had fought Corsairs and Hellcats in the Philippines and Formosa campaigns recognized the accuracy of the assessment immediately. They had experienced firsthand the overwhelming firepower advantage American fighters possessed. They had watched squadron mates disintegrate under Corsair fire. They had attempted to engage American fighters that simply accelerated away, climbing to altitude where Japanese fighters couldn't follow due to inferior engine performance and loss of control authority at high speeds. Lieutenant Saburo Sakai, one of Japan's highest-scoring aces with over 60 victories accumulated since 1942, reviewed the Kasumigaura report in late April. He had fought American fighters continuously, from the Guadalcanal campaign through the current defense of the home islands. His assessment was blunt and uncompromising. Everything in this report is accurate. I have fought Corsairs over Guadalcanal, Rabaul, the Philippines, and Formosa. The firepower advantage is exactly as described. I watched a Shiden take a burst from a Corsair during combat over Formosa in January. The aircraft broke apart completely in mid-air, not damaged, destroyed. The pilot had no chance to bail out. The aircraft simply ceased to exist as a functional machine. I have attempted to engage Corsairs in what should have been favorable positions, with altitude advantage and surprise, and watched them accelerate away faster than I could follow. Our fighters lack the power to catch them in level flight or climbing. The only way to kill a Corsair is to surprise it so completely that the pilot has no opportunity to use his speed advantage or to trap it in a situation where escape is impossible. Both scenarios are increasingly rare as American pilots gain experience. The armament disparity makes every engagement heavily weighted in American favor. When I flew Zeros in 1942, I could maneuver for position, achieve a good angle, and fire a precise burst that would destroy an American aircraft. Now, American pilots do not need precise aim. They point in the general direction and fire. The volume of bullets is such that something will hit. Our aircraft cannot absorb hits. They are destroyed. Sakai's comments were included in training materials, but with limited distribution. High Command worried that too much emphasis on American technical superiority would damage pilot morale at a time when Japan desperately needed every pilot to fight with maximum aggression regardless of the odds. The strategic situation in April 1945 left little room for careful tactical adjustments based on technical intelligence. American carrier groups operated off the Japanese coast with near impunity. B-29 Superfortress bombers attacked Japanese cities every night, incinerating urban areas with incendiary bombs. The Imperial Navy had lost most of its carriers and experienced pilots at the battles of the Philippine Sea and Leyte Gulf. The remnants of Japanese naval aviation were being organized for suicide attacks, where technical assessments of enemy fighter capabilities became irrelevant. Kamikaze pilots would not be maneuvering against Corsairs in conventional aerial combat. They would be flying into concentrated anti-aircraft fire and fighter screens, hoping to reach American ships before being shot down. For these missions, understanding the Corsairs' technical specifications mattered little. The pilots were not expected to survive regardless of American fighter performance. But the Kasumigaura intelligence team continued their detailed analysis of the captured Corsair because institutional knowledge would matter for Japan's eventual recovery and because understanding how the Americans had achieved such overwhelming technical superiority might inform reconstruction after the inevitable defeat. The engineering team's comprehensive report revealed patterns that extended far beyond military aviation. The Americans had designed the entire fighter around specific operational requirements derived from studying the realities of industrial warfare. Maximum firepower to ensure quick kills and minimize pilot exposure to return fire. Maximum speed to control engagement terms and enable pursuit of fleeing enemies. Maximum durability to maintain operational readiness despite battle damage and harsh operating conditions. Simplicity of maintenance to reduce logistics burden and enable operations with minimally trained personnel. Production efficiency to enable mass manufacture using standardized components and semi-skilled labor. These priorities shaped every design decision from the initial concept through final production. The result was an aircraft optimized for the realities of sustained combat operations across thousands of miles of ocean, with hundreds of aircraft in action daily, requiring massive logistical support and constant replacement of losses. Japanese fighters had been designed around entirely different priorities that reflected different assumptions about warfare. Maximum maneuverability to enable skilled pilots to defeat numerically superior enemies through superior tactics. Minimum weight to maximize range for escort missions and enable operations from remote island bases with limited facilities. Elegant engineering that used minimal materials to achieve required performance. Individual pilot skill was assumed to overcome technical deficiencies. These priorities had produced excellent aircraft for the specific scenario Japan expected to fight, a short, decisive war where quality would overcome quantity and where skilled pilots would exploit superior aircraft performance to achieve victory. But the actual war that developed bore no resemblance to Japanese planning assumptions. Industrial warfare was not about specific engagement scenarios or individual pilot skill. It was about sustained operations across an entire ocean, with hundreds of aircraft in combat daily, requiring logistics chains that stretched thousands of miles and demanding constant replacement of aircraft and pilots lost to all causes. The Corsair was designed for this type of warfare. The Zero was not. The ammunition capacity comparison illustrated the fundamental difference in design philosophy with brutal clarity. A Zero carried approximately 1,200 rounds total for both machine guns and 120 rounds total for both cannon. Total weight of this ammunition load was approximately 240 pounds. Firing time for machine guns was approximately 33 seconds continuous. Firing time for cannon was approximately 14 seconds continuous. A Corsair carried 2,350 rounds for its 6 machine guns. Total weight of this ammunition load was approximately 640 pounds. Firing time was 30 seconds continuous for all 6 guns simultaneously. The American fighter carried more than twice the ammunition weight, despite already being significantly heavier than the Zero. The designers had accepted the weight penalty because they understood that industrial warfare required ammunition capacity sufficient for multiple engagements without reloading. A Corsair pilot could engage 3 or 4 separate targets in a single mission and still have ammunition remaining. The ability to prosecute multiple engagements without returning to base for reloading provided enormous tactical flexibility. Combat air patrol missions could extend for hours. Fighter sweeps could engage multiple enemy formations. Ground attack missions could strafe multiple targets. A Zero pilot had to be extremely conservative with ammunition, taking only high-probability shots because running out of ammunition meant becoming defenseless. After 2 or 3 engagements, even if the pilot was victorious, he had to return to base to rearm. This limited the effectiveness of long-range missions and reduced tactical flexibility. The rate of fire comparison magnified the ammunition advantage even further. The Zero's cannon fired approximately 500 rounds per minute combined. The machine guns added approximately 1,000 rounds per minute. Total rate of fire was approximately 1,500 rounds per minute from all 4 weapons. The Corsair's 6 machine guns delivered 4,800 rounds per minute, more than 3 times the Zero's total output. In practical terms, a 5-second Corsair burst delivered 400 bullets. To deliver 400 bullets, a Zero would need to fire both machine guns continuously for 14 seconds, assuming no stoppages or jams. The cannon, even if the ammunition supply allowed, could only fire for 14 seconds total before exhaustion regardless of targeting requirements. Engineering analysis of the guns themselves revealed additional disparities that explained reliability differences. The Browning .50 caliber machine gun was a mature design that had been refined through decades of development and millions of rounds of testing. John Moses Browning had designed the weapon in the years immediately following World War I, and the basic mechanism had proven sound, and from the beginning. The weapon used a simple short recoil operating system that functioned reliably under harsh conditions. Japanese aircraft guns, particularly the Type 99 cannon, were mechanically complex and prone to jamming. The ammunition feed system required careful maintenance. Pilots frequently complained about gun failures during combat. The reliability difference reflected fundamental design philosophies. American guns were designed to function reliably in the hands of average soldiers with basic training. Japanese guns were designed as precision instruments requiring skilled maintenance and careful operation. In field conditions with limited maintenance time and inexperienced ground crews, reliability suffered dramatically. The captured Corsair remained at Kasumigaura through April and early May 1945. Genda flew it several additional times, evaluating specific performance aspects. Other experienced test pilots flew the aircraft to provide independent assessments. The consensus remained unanimous. The Corsair represented combat capability that Japanese fighters could not match. On May 23, 1945, American reconnaissance aircraft photographed Kasumigaura airfield from high altitude. Intelligence analysts examining the photos noted what appeared to be a Corsair among the Japanese aircraft. The assessment was accurate but militarily irrelevant by this stage of the war. Post-war interviews with Japanese engineers who examined the captured Corsair revealed lasting impact. "We understood that we had lost not just a war, but a fundamental contest of industrial philosophies," one engineer recalled. The Americans designed weapons that could be produced in vast quantities, maintained by inexperienced personnel, and operated successfully by adequately trained pilots. "We designed weapons requiring exceptional pilots and skilled maintenance." In sustained warfare, the American approach proved overwhelmingly superior. The captured Corsair was destroyed during an American air raid in late July 1945. The intelligence value it provided survived in detailed reports documenting Japanese engineers and pilots confronting America's industrial dominance. The specifications had seemed impossible: 650 caliber machine guns, 4,800 rounds per minute. But Genda had flown it. He had fired the guns. The specifications were engineering reality, backed by American industrial capacity and design philosophy. Japanese pilots had refused to believe it until evidence became undeniable. By then, the war was already lost. The lesson learned too late was that industrial warfare was decided not by individual warrior skill, but by the ability to produce overwhelming quantities of effective weapons and employ them systematically. The Americans had mastered this. Japan had not. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.